Welcome back to the Algebraic Graph Theory Seminar. Our speaker this week is Bojan Mohar from Simon Fraser University, and he'll be talking about the smallest eigenvalue separation for non-bipartite graphs.
Okay, thank you. This is a little topic I came to by more by accident than by searching for it, but it turned out to be a nice little result. And I decided to speak about this as I was listening to a lecture of Sebi Choba 2 weeks ago in this open problem session that you held during that week. And he was mentioning this result, and I thought maybe it's a good time to to popularize it a little bit and do some more research what else it could give. So what's the basic setup here is we look at the smallest eigenvalue of a graph, and we look how it is related to a graph being bipartite. So let me start with the basic notation. Throughout the talk, n will always stand for the order of the graph, the number of vertices. And all eigenvalues will be with respect to the adjacency matrix A of G, ordered in the decreasing order. And there are actually just two of them that I will be interested in, and it's the largest and the smallest one. So the largest one is known as the spectral radius, and I will use a notation lambda for the smallest eigenvalue. So some people also use lambda sub mean of G or so, but here we will use this throughout, and this will lambda of G just denotes the smallest eigenvalue. Now, I'm assuming the audience here is familiar with the basic properties of eigenvalues. Just remind you that the Perron-Frobenius theorem has as a corollary that the spectral radius is equal to actually the largest positive eigenvalue of a graph. And in particular, it's at least as large as the absolute value of the smallest eigenvalue. So there is an addition to Perron-Frobenius, which says if a graph G is connected, then actually the largest eigenvalue is simple, and it's also the largest eigenvalue in the modulus unless graph is bipartite. So there is a simple characterization which says that a graph is bipartite if and only if a connected graph is bipartite, if and only if its smallest eigenvalue has the same magnitude as its largest eigenvalue. Now, the common theme of today's talk will be, what can we say if a graph is not bipartite? So in that case, lambda must be smaller than the spectral radius. How much smaller? So this is what I will call a negative spectral gap. So we look at, I will just use for the purpose of this talk, lowercase delta of G, or just delta, to be this gap between minus spectral radius and the smallest eigenvalue. So if you look at the gap between the between this smallest, the negative of this is just equal to the value lambda plus rho, and this is a non-negative number. That's what we know. Let me just remind you about Hoffmann's eigenvalue bound, which basically says what I have asked. It says that if this gap is large, then the graph must have large chromatic number. So what's the corresponding theorem is actually, which says that the chromatic number of a graph G is at least 2 plus delta divided by this magnitude of lambda. So you see, if delta is non-zero, then this is positive. So the chromatic number is at least 3, because it's strictly bigger than 2. But it could be as well much bigger. For instance, it is strong enough to say that the complete graph, for the complete graph, the chromatic number is at least n. So that what this Hoffmann's bound in this primitive version would imply. Now, I should mention original motivation, how I came to this setup. There was a few years ago, there was a paper by Jack Cullen and Kiao, and they proved the following result. So they proved 2 results, one in 2017 and then an extended version in 2 years later. So the first one said that the following: for every constant d, g, k, and epsilon, so d would be a diameter, g would be odd girth, and k would be a degree. There exists only finitely many distance regular graphs with diameter d, degree k, odd girth g, and the smallest eigenvalue, or at least say this spectral gap of g smaller than epsilon times k. So it says that basically the smallest eigenvalue of and non-bipartite. Yeah, this is a consequence of odd girth being finite. So there exists usually this spectral gap will be larger than a constant times k, so the value of the largest eigenvalue. And in this second extension, they proved the following version: for every g, there exists an epsilon, a positive real number, such that now every distance regular graph G with parameters as above, so I will not repeat. Diameter will be excluded now, but degree K and odd girth G, at least G, satisfies that delta of G is big. So this is independent of the degree. So for all degrees, same epsilon. Epsilon only depends on the odd girth. If you just to remind everyone, so what is odd girth? This is the length of a shortest odd cycle in G. So you don't care about short cycles of even length. There could be tons of 4 cycles, 6 cycles, and so on, just caring about the shortest length of the shortest odd cycle. And you see you get this separation, which is which says that the positive fraction of the is actually the spectral negative spectral gap has a positive fraction of the spectral radius. Now, when I saw this paper, I was discussing with my postdoc, Fiachra Knox, and we both said, well, what's going on? So why is this so complicated? And basically, we found a simplified proof. Let me just show you that. Let me just show you the paper where this appeared. So this is the paper by Kiao, Ying, and Kulan, and they proved two theorems. So the first theorem is the one I've mentioned, and the second one is actually giving a specific version what this what would be graphs, so distance regular graphs, for which these negative spectral gap would be really small. So, and what they have smaller than 1 over the diameter times k. And they characterize these graphs. Of course, this characterization is not easy, but theorem 1 proves to be possible to get much simpler proof. So here you can see the proof of theorem 1 takes almost 2-3 pages, and it's takes a lot of ingredients from algebraic graph theory. So all these parameters of distance regular graphs, certain algebraic properties, the Villiger algebras, and so on. So that's just for this. And I want to go back and continue with what we got. So we saw that, and we looked at this, and basically what it turns out that this epsilon times k, this is the consequence of the fact that there are plenty, that there is not just one odd cycles of length g, but there are plenty of odd cycles of length g in distance regular graphs. If you would have just one, you couldn't get such a separation result. So because you could have a huge bipartite graph and just one odd cycle somewhere, and that wouldn't give much of a difference. So we found a more general result, which is not only has a short proof, but it's also what we think it's tight. And the main idea in the proof was the following. So here is something that you could consider, but it doesn't give a satisfactory result in this manner. But just suppose that you can partition the edges of your graph as E1 union E2 into R parts, and consider the corresponding adjacency matrices. So then you can write the adjacency matrix of the graph as the, I guess this is a mistake here. It must be a plus here. So you can write the adjacency matrix as the sum of the adjacency matrices of those. And of course, in some nice situations, you may have that the spectral radius of A is just the sum of the largest eigenvalues of this. Certainly, it's never bigger, but you may have that also the smallest eigenvalue is close to the sum of the smallest eigenvalues of this. And in that case, the spectral gap would be roughly the sum of the spectral gaps. So if you look back at this result, so here you can think of this epsilon to be spectral gap of a cycle of a cycle of length g, which is odd, and that would be roughly spectral gap would be roughly 1 over g. And so this would be, you could take epsilon is 1 over g for this case. So here this idea suggests that 1 over g could possibly be a result. Now, we can't profit with that, but it works with a little bit more general situation, which I ended up calling fractional decomposition. So first of all, suppose that if you have a partition of edges into the subsets, then you say this is a decomposition. But the fractional decomposition is that you assign weights to every subset, E1 up to ER, and then you demand that every edge is in at least is maybe in many of these graphs, but altogether the sum of the weights is at least 1 or equal to 1. So let me, this is a common notation for such a situation. So you can say GI is the subgraph. If GI is the subgraph with the edge set E sub I, then you can write G as being the sum of weighted graphs, so the sum of alpha I times GI. This is sometimes called a quantum graph. So it's a kind of a notion that many people from this seminar investigate with respect to the walks-in graphs. But anyway, so you can call this a quantum graph or a fractional decomposition. And the nice feature of this is that the adjacency matrix of the graph is actually equal to the sum of the weighted sum of these adjacency matrices of these subgraphs. Now, suppose I have such a fractional decomposition, and usually these subgraphs will contain just a certain number of vertices of positive degree. Maybe this is a short cycle, a triangle in a graph, and all other vertices will be of degree 0. That's why here I will use this notation. So just remember, if I say instead of G sub I prime, this is the same graph except that I removed all isolated vertices. So let me give an example. Here it's maybe a picture. I'll take this graph on 10 vertices, which some people call it's like a prism. So it has this so it has an odd cycle here, a cycle of length 5, another cycle of length 5, and then a double matching joining these two cycles. So if you take in this graph, if you take all, let's consider this as a planar graph, and then take all faces as the subgraphs G1. So G1 will be this pentagon corresponding to the outer face. G2 would be the pentagon corresponding to the inner face, and the others will be triangles. And if I put the weight 1/2 to each of them, then you see every edge is contained in precisely 2 of these graphs, and 1/2 plus 1/2 is 1. So this is the condition for the fractional decomposition. So this 2 C5s and these 10 cycles of length 3 form a fractional decomposition of our graph with weights 1/2. So, and this decomposition has a nice feature, which is it's a kind of homogeneous. And homogeneous means the following: if you look at any vertex, what you will find 3 subgraphs isomorphic to this H2. So 3 triangles. This one, and the one here. So these 3 triangles containing the vertex, and 1 pentagon containing that vertex. And every vertex has the same feature. So it's basically here I have 2 types of graphs. One is a pentagon and one is a triangle. And I have a fractional decomposition into copies of these graphs. And each vertex has the feature that it is adjacent to the same number of C5s and the same number of C3s. Well, here by the number, I don't really mean the number. I want that the sum of the weights of this is the same. So if I look at this, the weights corresponding to H2, let's say, it's every vertex has 3, so 1/2 plus 1/2 plus 1/2, so has weight 3 halves associated with, oh, that would be S2, I guess. And this one would be S1. So the number, the sum of the weights of the graph H2 such that the copies containing my vertex V sums up to 3 halves. So this sum is the same for every vertex. And for the second type of the graph, H1 here, the C5, you see every vertex is contained in precisely one of them, and both have weight 1, 2. So we again for H1 is C5, we get this sum S1 to be equal to 1/2 for every vertex V. Now, when this happens for every vertex V, we say that this fractional decomposition is homogeneous. Is this clear from the example at least? So what we want to know is, I will say in how many, but I mean with the weights, in the weighted sense. So for each vertex, the number, so the sum of the weights of the first type of the graphs is the same, and of the second type is the same. And so for every, in general, if you have, instead of 2, you may have T types of these subgraphs. An additional condition here is that all these subgraphs will need to be regular. So same degree D sub j. So D sub j regular. And that will also imply that the graph itself it's regular. Okay, so that's a definition. That's a basic definition what a homogeneous fractional decomposition means. Now, if you have such a homogeneous fractional decomposition where dj is, so this would be, I think I need to put the j here. So dj is the degree of the jth graph, and then it turns out if you go over j equals 1 up to t, so over h1 up to ht, these numbers sj that were part of the definition of the homogeneous fractional decomposition give us this formula. It says that the degrees multiplied with these weight coefficients sum up to the degree of the vertices in G. So K is the sum of the degrees of the vertices in G. A proof of this fact is just a simple double counting and using the definition. So you use that this sum of alphas for each edge is equal to 1. That was part of the fractional decomposition. And then you use that this sum of the alphas over each for each I over all edges is just a multiple of dj. So this Sj, and then you come up to the formula. I won't go into details because it's just a simple double counting. Now the main result here is that the intended theorem that the negative spectral gap of the graph is larger than roughly the sum of the spectral gaps of the particular graphs that we have there. So and the weights, it's a weighted sense. The weights come from this homogeneous constants S sub j. If I go back a little bit, so if I just pull back a little bit to explain this, on this example, it will say that the negative spectral gap, so this graph is 4 regular, so the difference between the smallest eigenvalue of this graph and -4 is at least, so we get S2 times it's 3/2 times the spectral gap of C3 plus 1/2 spectral gap of C5. Spectral gap of C3 is 1, so this is 3/2. Sorry, C3, yeah, the negative smallest eigenvalue is -2, and sorry, the degree is 2, the largest is 2, and the smallest eigenvalue is -1, and then this is plus 1/2 spectral gap of C5. So it's almost 2, as you see. Now I'd like to spend a minute just explaining the proof of this. It's a simple proof, but all ingredients are somehow necessary, and it goes as you would think it should go. You take an eigenvector for the smallest eigenvalue of the graph G. Let's say it's of norm 1. And then you take values of this eigenvector on the subgraphs. Now, GI would be a subgraph, but I mentioned that we delete isolated vertices from GI. And so also when we say the eigenvector X adjusted to this subgraph, we just delete the values of this vector corresponding to the isolated vertices. So those are just removed. So just the restriction of the vector to the vertices of GI prime. So this eigenvector can have, in general, it will have smaller norm than 1, maybe even a lot smaller. But the following is still true. If you take the quadratic form, the adjacency matrix of this GI prime on, well, this would be on GI. I can put it prime here for GI prime. It's actually the same matrix because we just deleted the zeros corresponding to the isolated vertices. So this quadratic form, which gives us an upper bound on the smallest eigenvalue. So we'll say that the quadratic form is at least as large as the smallest eigenvalue of this AI prime. This is the same as A prime. So the smallest eigenvalue of GI prime times the sum of the squares, so times the norm of this vector, which is which could be smaller than 1, as I mentioned. Now, how can we use that? So, but you see, now we just use this inequality, and look at the smallest eigenvalue of G, which is by definition of X, equal to this value of this quadratic form, AX dot X. And if you use that A is the sum of alpha I AI, just use linearity of the inner product, you get that this is the sum over all I of alpha I times the quadratic form for AI. And here we use the upper inequality, which says that this is at least lambda I times the norm of this smaller vector xi. Now, here is a trick why everything works. So now you try to, instead of taking the sum over all I, you just take the sum over all. You remember these two graphs, H2, H1, and H2. So just on the types of these subgraphs. So you look at each subgraph H sub j, and then split the sum from 1 up to r, going first over all j, and then over all I, such that gi prime is isomorphic to this H sub j. So this is the same sum as I1 up to r. And now look at it in this double sum. You look at this little sum of vertices only in VI. And now, so here is that this sum is shorter. It doesn't contain all coordinates of the vector x. But because of the homogeneity, the x sub v in this triple sum appears the same number of times for every vertex v. And this is just together with the weights alpha I, this is just what it comes from the definition of those numbers S sub j. So this is in our first lemma. So this is saying that again, every x for every v, x v squared appears as j times. Well, when taking these weights alpha I into account. So this is why we get a different sum, and this different summation is only over the subgraphs H1, H2 up to HT. So J goes from 1 up to T. And here is the sum over all vertices, not over VI. So that's important. This sum is 1, so this is a vector of norm 1, so it comes out. And then we just express lambda and delta with the degrees, and this is a simple verification that this gives. So what we get is that, you see, if you put lambda plus k on the other side, you get delta of g is at least the sum of deltas of these subgraphs, which we were needed to prove. So the main ingredient here was that this summation here was able to go through because of the definition of homogeneous fractional decomposition. Now, how does that work on distance regular graphs? Let me just mention that if you have a distance regular graph, it has a homogeneous fractional decomposition into copies of a single graph, which is just a cycle of length 2h plus 1. So how does that work? Let's look at any vertex here. So distance regular graphs, it may have lots of short cycles. So there could be short cycles of length 4 and so on. Okay, my picture won't be nice, but if I look at cycles of length G, they will look like following. So we come here, and then we have an edge on the same level. So this is distance h. So all cycles of length h look like that. And from every vertex, you get basically the same number of such cycles. Why would that be? Well, if you look at the distance partition of your graph, you know that distance regular means, in particular, that here it's a regular graph. So you can count how many, the number of these chords here is equal to the number of the cycles of length 2h plus 1 containing V. So you see, basically, you see that, oh no, that's not the same. That's not exactly true. This would be true if this wouldn't be odd girth, right? This would be true if it would be even girth, but you may get one of this may give you another one. So let's look at this one. Well, it gives you this cycle, but it also gives you this one of the same length, and here, going here. Well, it's not equal, but it's proportional to that. So it's number of chords, it's proportional to the number of these cycles. And it turns out easily, just using the parameters of the distance regular graph, that this proportional is the same for every vertex V. You can express it with the intersection array of the graph. So what it means is that it implies that it's even more that every edge is contained in the same number of such cycles. And then this gives you a homogeneous fractional decomposition. So that's, I was very sketchy here, but people who understand distance regular graphs much better than me surely see what the proof is. So using that, we can get the lower bound on the fractional, on this spectral, negative spectral gap. So if I have such a non-bipartite distance regular graph, I just use the previous theorem, which says that delta of G is at least, so there was the sum of these deltas. So this is just one graph. It's just the cycle times this S sub J. Well, it's S1, which is, I guess, equal to 1, or maybe 1/2, I guess. It's 1/2, yeah. So S1 times delta of C2H plus 1. The cycle of length 2H plus 1 has the smallest eigenvalue, which is twice this cosinus. And so this is a difference between 2 minus twice. S1, I think it is 1/2. So that's why you just get, instead of 2 minus twice the cosinus, you get 1 minus cosinus of pi. So it's just the smallest value of that. And that's roughly 1 over 2h. So it's roughly pi over 2h plus 1. Times k. very explicit and very direct bound. Okay, maybe I should mention some more consequences. Let me start with one that you all familiar with, line graph. So if I take a line graph, then each vertex in a line graph, well, let me think of this being a edge E. Maybe it's of degree 3. So in the line graph, this vertex will be adjacent with a clique of size 3 and a clique of size 4. So you can think of this cliques. So let's say this is a bipartite, semi-regular bipartite graph. Degrees D1 and D2. And then each vertex will be adjacent to a complete graph. So H1 would be a complete graph of size D1, and H2 would be the complete graph of order D2. And every vertex is adjacent to one of each, which makes this decomposition into these cliques being a nice homogeneous fractional decomposition. If you have just a regular graph, not necessarily bipartite, then you can just do so the line graph of K regular graph would have a fractional decomposition into the copies of H, which is just a complete graph of a size K. So let me just mention delta of H is, so the smallest eigenvalue is K minus 1. So this is lambda plus rho. So the largest one is K minus 1, and the smallest one is minus 1, which is K minus 2. So that's, this is the negative spectral gap of H. And then by the theorem, sorry to go back, the spectral gap of the line graph will be at least, again, we have this constant, which is 1/2, I guess, here. So the spectral gap of the line graph of G, K regular graph G, will be at least, well, this is this S times K minus 2. I think S is 2 in this case, so which is 2 times K minus 2. Let's see, what is the line graph of a K regular graph? So line graph of a K regular graph is rho equal, so line graph, every vertex is of degree 2K minus 2. And smallest eigenvalue, it's a line graph, so it's minus 2. So rho plus lambda is 2K minus 4. So it's, you see, this is pretty tight in this example, and so it was in some other examples. You can get a pretty tight example also as following. This one is actually the one which says that there is no possibility of doing it. So you just take a regular a cycle, odd cycle of length G, of odd length G, and then take a blow up, just a blow up of this, replace every vertex by an independent set, and put a complete bipartite graph here. So this has certainly a fractional decomposition, because you just take all of these cycles, if you want, just that go once around. So all such possible cycles form a homogeneous fractional decomposition, and you can compute the parameters, and you see that this is tight. So here you get really, you can't do any better than this example shows. I guess I ran out of pages, so I will. It's a good time to stop now, and I'm all yours for questions. Thank you very much.
Thank you for the nice talk. Are there questions?
I have a quick question. So Bojan, did you know there is this paper by Trevisan with kind of like a analog of the isoperimetric inequality, but for lambda n. Are there like these bounds that you get from this method? I mean, comparable could be with, they have he has a different quantity. Like he has this measure of bipartiteness, beta of G. It's like more complicated. I don't know if you looked into it to see if it's.
No, I didn't, and I don't think it is. But it's so it's like, I mean, one thing is that if you look at the lambda n, that's related to the largest eigenvalue of the complement, right? If the graph is regular, let's say, or so it's. I would say that this would be the closer relationship to that.
Uh-huh.
Yeah. This one does. You see, if you would think of using that for this distance regular case, you wouldn't be able to do that.
No, for sure, because that parameter, like, so the parameter that they have, I try to figure it out even for some simple graph, and it's not easy. Like it's it's definitely much more complicated than this decomposition into cycles and so on.
Right. Yeah. Yeah. I don't. I haven't seen that. I mean, it's Hoffmann's inequality, and then there are versions of Hoffmann where you take something similar as Lovász does for Lovász theta function, where you can put entries, arbitrary entries for non-edges and optimize, right?
Mm-hmm.
So that's another thing which is, but it's not the same. It's totally different. So that goes, that tries to say, if this negative gap is large, what can I say about the graph? So I was saying different. I was saying, well, if the graph is non-bipartite and at least locally everywhere it's the same measure of non-bipartiteness, right? Mm-hmm, so it's not like it would be an odd cycle just in some little part of the graph.
Mm-hmm.
Then this cannot be too close to the minus spectral radius, right?
Yeah.
Yeah.
Okay. Thank you.
Yeah, Chris is checking if there is something like this in the Erdős-Corrado book. Is it, Chris?
Well, no, but I think this decomposition idea has been used before.
Must
so
be, I
that's
guess.
what I was thinking about. Yeah, I think Mike
Even
Newman
for eigenvalues, was it? Or?
Yeah, well, Mike's lurking here. I thought Mike Newman had an argument we used at some point. But anyway, that was.
I don't recall anything exactly like that.
No, it wasn't exactly. I mean, but I remember seeing some argument we were writing that Jason G matrix was being written as a, as a sum, but then divided by multiplicity. So as a fractional linear combination of cakes or something. That was all.
Yeah, that sounds familiar.
Yeah.
Mhm.
So I was just trying to see if I could find it before I said anything.
Yeah. I mean, if you prefer integers, you can also think of integer decomposition. You just take multiple edges. So just
Oh, yeah.
multiply the
yeah.
edges, and then you have the usual decomposition of edges, right? So
Yeah,
just
yeah.